In this lesson, we're looking at sample proportions. Now, in a binomial experiment that has n Bernoulli trials, just like the sorts of experiments that we've been looking at in this whole chapter, each of them has a probability of success p. The sample proportion is just this. It's literally the proportion of those trials that were successes. So we've got a little formula for it here. Any one thing that could happen, if we just divide by the total number of things that could happen, we're going to get our proportion. Now, some formulas here, warning, they're not on your reference sheet, whereas the ones that we used in our previous exercise were. We get a quite straightforward result here. The expected value of the proportion is just the probability itself. So if I've got some experiment, say, where I'm flipping a coin and the probability of heads is exactly a half, then P is equal to half. Now, if I flip the coin 20 times, the expected value for the number of heads I'm likely to get is going to be 10, because out of 20 flips, I'm expecting about half of them will be heads. So the expected value as an outcome is 10. But the expected proportion of the coin flips that I'm expecting to be heads is a half. So that's how we use this here. Literally, a half is what I'm expecting to be the proportion of heads that I get, if that makes sense. So this is actually a really simple concept. We've got to try not to overthink it. Now, we can also look at all of the proportions that could happen. Now, instead of thinking of the outcomes that could happen, if I'm flipping a coin 20 times and looking at the number of heads I could get, then X could take the value of 0, 1, 2, 3, anything up to 20. But the proportion of the coin flips that are heads could be anything from 0/20ths, 1/20th, 2/20ths, does that make sense? All the way up to 20/20ths. So we're literally just looking at what the number of heads will be as a fraction of the total number of trials. So what we're expecting is half of the coin flips would be heads. But we can also then look at all of those proportions, which are now a bunch of fractions instead of integers, and we can find the variance of those numbers and the standard deviation of those numbers. Now, we get this formula PQ over N because if we take the variance of the proportion, that's really just the variance of, I should have put another line in there, the variance of X over N, because that's what the proportion actually is. And that gives us the variance of X over N squared. So a bit of a weird thing happens in the formula there, which we know that the variance is just NPQ over N squared, and that tidies up to be PQ over N. We can also find the standard deviation of that simply just by taking the square root of that, or we could write it this way round, where perhaps this one is a little more intuitive because this is the standard deviation of X, and here you're just dividing it by N. So perhaps if we memorize this one, considering these aren't on our formula sheet, and know that for X, we know that the mean is NP, and we know that the standard deviation is the square root of NPQ. Well, now we're learning that for the proportion of the trials that were successes, we can see that mu, or the expected value, is actually just P. So that's really simple. And, let's write mu equals P. And the standard deviation is exactly what it was above there, but it's just we're dividing by N because we're literally saying, well, what proportion of all of the trials were those? So I think that is probably a simple way to remember it. This is an understanding thing, and this is just taking this one and saying, well, we'll divide by N. And probably writing these down in your book is a good idea, and we can see where they come from. But at the end of the day, we've just got to keep it simple and divide by N. Now, the probability of any particular portion equals the probability of that corresponding X value, which means that some questions using proportions can be answered using techniques that we learned previously, and you don't even need any of this, whereas other questions are going to require these formulas here just to make our working a little bit easier. Now, what do I mean by this sentence? Well, if I'm flipping that coin 20 times and looking at how many heads I get, then if I say, well, what's the probability that I get exactly 12 heads? I could work that out using the methods that I've already looked at without my binomial probability. If I said, what's the probability that I get at least 12 heads, then we've looked at how we could approximate that using the normal distribution, and we could either correct for the data not being continuous or not, and that will give us two slightly different answers. One is better than the other. It's, I think, better to correct. Or we could say, hey, instead of looking at the probability that we get 12 heads or more, let's look at the probability that the proportion of heads we get is 12/20ths. Does that make sense? Because the proportion of heads that we're interested in would be 12/20. That's literally the only difference in what we're doing today compared with what we did in the last lesson. Now, I think the easiest way to understand what it is that we're doing in this lesson with the proportions is to look at this really simple example. I've written virtually the same question here twice, and we're just doing it 2 different ways. A coin is tossed 6 times and the number of heads is counted. Where here we're saying that x is the number of heads that we got out of 6. So clearly the scores that x could take vary from 0 to 6, and we've got the probabilities, we know how to work those out using our basic binomial techniques, are written there. So our formulas here, which are on our formula sheet, the expected value of x is 3. That means we're expecting to get 3 heads out of 6. And the variance of how many heads we might get is 1.5, and we can take the square root of that to find the standard deviation. And again, this formula, NPQ, is on our formula sheet. So then what is P with this little acute sign on top of it? Well, if a coin is tossed 6 times and the proportion of the tosses that are heads is found, that is the proportion of the tosses that are heads. Now, if we're expecting 3 out of the 6 to be heads, then the proportion of the tosses that we're expecting to be heads is half of them. So it's very easy to understand, I think, that the expected value of this proportion is just P, and that's just a half. We're expecting half of the tosses to be heads. And you can see here that all of these probabilities for what might happen in terms of the number of heads we might get are the exact same probabilities that we have down here when we're saying, hey, what's the probability that the proportion is a certain thing? Well, here, the proportions, we might get 0 out of 6 being heads, 1 out of 6 heads, 2 out of 6, 3 out of 6. So we're literally just defining the proportion as the proportion of heads that we get out of 6. And we've got all the same outcomes, all the same probabilities, we're just looking at the same question a different way. Our formulas are slightly different here though for the variance of the proportion. We've got PQ over N, so we get 1/24th, and the standard deviation of the proportion is the square root of that. So think about what this means. This means we're expecting half of the scores, or half of the tosses to be heads, and when we look at how that might vary and how spread out the possibilities are, the standard deviation of how spread out that expected proportion might be is this. So I think you can see now why maybe some of the questions can be done 2 ways, depending on whether you're thinking about the number of outcomes you're expecting or the proportion of the outcomes that are a certain way. It really depends on just how you define the question. Now, we're not going to use this data here in our first example to look at how we would use the methods that we need for this exercise. The reason is we're only tossing this coin 6 times. So if we want to find the probability of getting 4 or more heads, or the probability that the number of heads we got was 4/6 or more, say, because the number of tosses is so small, we need to just use basic binomial probability techniques for that. If we were doing the probability that we get 4 or more heads, we'd say the probability of 4 plus the probability of 5 plus the probability of 6. That would be 3 terms. Each one of them would be a term of the binomial expansion, which is half plus a half all to the power of 6, and we'd just find it that way. We would not use this scenario to approximate this distribution to a normal distribution, because with so few tosses, it really isn't going to approximate a normal distribution very well at all. So the questions that we'll look at will use many more tosses than that. And remember, we've got that rule of thumb that the number of experiments, or n, multiplied by p, which in this case we've got 6 times half is only 3, needs to be at least 5 for us to have any chance of saying it's a good approximation to use the normal distribution.